Everyone putting it down.
Recording?
Yeah. Well, we're 5 minutes in, so maybe we can just get started. Oh, this one. Hello.
Just let me know if you want to be started.
Okay. Yeah. Well, yeah, it is 5 minutes, so maybe you can start it. So everyone, please welcome Sean Ma. Today he'll be sharing his research with us about optimizing computational architectures. So yeah, Sean Ma, please take a look.
Okay. Yeah. Hi everyone. So I'm going to introduce the research I'm doing and involving today. So the first, I would like to thank you, the school, to give me such an opportunity to our new staff members to give a presentation in a small light. So I know most of you has been aware of the AI, and the AI is now changing the world periodically, largely, and not to mention about the research directions and works we're doing, right? So it got impact a lot, and the resource all over the world actually, such as some computation powers, are also shifting towards the AI or artificial intelligence. So AI actually got popularized maybe just less than decades ago, but here, but have you heard of any new computation architecture dedicated for the AI for recent years? I don't think so, because most of the computation platforms we're using right now is GPU or graphic cards, right? So but they were designed mainly for gaming or 3D modeling not long ago, right? So we know that we need probably a promote or fast response neural networks model based on the computation architecture with less overhead operations. So this is our ideal ideas to achieve. So now we have a dilemma arise. So here we can change these algorithms of neural networks models to fit the existing platform, such as GPUs, right? Or we can come up with a new platform, and that is more suitable for the current neural net models. So we basically have these two choices to do. So due to this fact, me and the PhD and master student at my supervision and the co-supervision actually choose the later one, and we're looking for an optimized platform for artificial intelligence. So into this meeting, I would like to give you just a very brief introduction about what we have done and what we will do. And the platform we're using currently, we call the FPGA. And this is how AI neural model is put. And then the second one is the topic is about how AI and neural network model is pushing our communication architecture to change until now. So the third one is my research program, my PhD or postgraduate students are doing, and I gave you some examples about what we have done and we will do in the future. So the last one, just one slide. Let's think about something about the future. So I don't know whether this research meeting is going to be formal, technical or not. So my select today is only just cover some basic ideas, basic things, and if you are interested in what we are doing, and just feel free to have a chat after this presentation. So first of all, the platform we're currently use, we call it FPGA. So it is short for the Field-Programmable Gate Array. And actually, I don't want to introduce this platform to the others by just simply giving these full names, because it often confuses people more than before. So just put into the human terms. So programming the FPGA actually can be treated as just doing something or design the circuit level things. So the circuit inside the FPGA are comprised of many basic units, such as we call the CLB, or short for configurable logic blocks. So here in this example, and yeah, probably okay. So we have these two, A, B, C, D, that full in as input. So by looking for the lookup table here, the IoT, so the final output can be determined by checking different switches or parameters based on those ones. So yeah, so the clock here we have probably have a clock, and normally this clock is a quite important signal to drive those sequential logics, because without those clocks, our output sometimes cannot go that far. And by introducing this clock, so we start to do everything when we meet this clock's rising age, and we finish our logic operations before the next clock rising age. So this is how we're going to do it. Something like tick-tock, something like that. So when we scale up this quantity of the CLBs or those configurable logic blocks, so what we can have finally? So we have a kind of like a two-dimensional array, basically based on these CLBs, and these blocks can be all programs and output different values and output the different values according to what input we gave and the setup parameters in every CLBs. So now I think those field-programmable gate array sounds much reasonable. And by manipulating those interconnections of these CLBs, we can easily, or sometimes probably not easily, so render every logic gate working in parallel or pipeline model as we wish. So probably there's another possible question, I guess. Like most of you probably may wonder if how we're going to build a circuit one logic gate by one logic gate, because it's kind of like if you want to build a very basic like operation like convolutional operations in AI inference. So what time? How long will it take? We cannot just do one logic by one logic, right? So no matter you have this doubt or not, so actually this is really a good question for us as well. So actually it is not what it looks like here. So there are some dedicated programming language. We call this hardware description language, or short for HDL. So so here I will give you a very basic example here. So say we want to have a 1-bit half adder. So this is a very basic adder. So what we need to do is we draw. Firstly, we probably we need to draw a truth table here, right? For every every input possibilities, and also their corresponding outputs, right? And we probably have some carries noted by C. They are based on these tables. We can draw a logic gate based function diagrams here, so shown below, right? And now we have the first code snippet written by one type of the hardware description language called Verilog. So it basically describes what input signals we have. So we have the A and B, right? So if you look into this code, we also have the input A and B, and what signals for the output here is C, right? The rest of the code is just only about the logic operations, 100% same as these logic diagrams on the right. And this is the first version, but actually is if you are dealing with those low-level programmings, you may think that it's just like writing an assembly language. Well, every logic operation has to be easily understood, but when we combine these logics, who knows they are meant for, right? We don't know what's going on when we connect them together. So in this slide, we have a kind of like another way to do this programming. We have a behavioral modeling. So we need to describe what do we want. Here, in the examples, we want to design one bit half adder. So we're going to write an equation directly. So in which we have a one addition operation for A and B, and the carry bit for C, and S is for the sum. So just one line of code. So much easier than before. But it's kind of like still too hard for my master students I'm supervising, because they prefer more advanced language or high-level language, at least C language. So here comes the more advanced one. It is called the high-level synthesis or HLS. So word high actually just comparably high. It's still circuit level oriented design or language. So it's basically C code, but there are still some electric design rules you need to be considered when you're really focusing on those or doing some research about this design. So even we already have this HLS language, you still need to consider a lot of things. So basically, there are kind of like we call the technology barrier when we're working on these FPGAs, but it's getting much better and better. So are there any practical designs so far related to FPGA? Of course, yes. So the most famous CPU designed and manufacturers Intel and AMD, after purchasing the FPGA companies respectively, one purchased Atara, the other purchased Xilinx. So they are fighting again in the FPGA field. So above this image, it is the Intel Xeon processor with the FPGA integrated, and the below one is from the AMD. they are trying to use to build an embedded processor with all together with the FPGA fabricate. So this is the practical designs recently. And what type of work FPGA can do? So here is a very basic examples for convolutional operations with binary ways and the binary activation. So the input here we have is this is a grid representing the input data to be convolutional neural network layers, right? In this diagram, the activation are all represented by -1 and the positive ones, suggesting that the use of the bipolar encoding, where probably the -1 represents 0 and those positive ones represent 1. So the kernel here refers to a kind of like a filter applied to the input activation during this convolution operations. So it also consists of the -1s and the positive ones. So we have a XOR operation. This is the bitwise operation stands for X through NOR. So when applied between this input activation and the kernel, it basically return 1 when both corresponding bits are same, and it returns -1 when they are different, right? So this step is very important in binary convolutions, as it simplifies the multiplication. We can just get rid of this multiplication, use this simply bitwise to help us do these convolution operations, which is kind of like we can reduce the complexity of the computation. So then we have the pop quant. So pop quant, as after applying this XNOR, the next step is to just count the numbers of positive ones we have in this resulting matrix, and this count gave a measure of how many elements between the kernel and the portion of the input it covers. So the final output of this process actually is not only about the pop count. It's also related to something we say the scaling and the normalizations based on the kernel size. So in the context of these binary networks, so the pop count result often need to be adjusted and reflect differences, such as in this situation we need to reflect the differences in count of the positive ones versus -1s. So which can be achieved by subtracting the count of the -1s from the count of the positive ones. And this is the pop count result. So here, this is the intermediate result we have after doing the XNOR. And then we connect how many positive ones we have, 1, 2, 3, 4, 5, and the negative ones there are 4 for them, right? So basically the result is 1. I forgot to mention all things. So this is the ideal scenarios, but practically, normally we will lose a lot of the information if we only use the binary ones, right? So in practically mixed precision scheme normally apply. So because sometimes those one is quite important, we need to maybe to keep all the informations. We probably use the most precision data type to represent those part of the information. And sometimes it's not important, we probably use this only binaries. Okay, so since there are too many restrictions about these FPGAs and also the technology barriers, right, when we're talking about the FPGAs, so why am I insisting on using FPGAs? Why? So am I sort of the PTSD or the OCD? No, of course not, because the second subtopic I'm going to say is about how AI pushing us to involve our computation architecture. So I'm going to use these 3 dimensions or three layers for every computation architecture I will introduce. So we have So we have a hardware layer. So it's talk about what kind of architecture we use. And the second is about the presentation layers. It means that how results and the outputs are displayed and managed. And third one is about the problem solving approach layer. So this refers to the conceptual and some methodologies you are using to tackle or approaches or algorithms and technologies are developed and applied. So here firstly we look back to the past. So what do we have done? So first one is the von Neumann architecture. It's widely used in the CPUs, right? So one of the things for von Neumann is it's a kind of like a strategy they are using is divide and conquer. So the divide conquer is a strategy when we're dealing with complex tasks and using computers. So for example, we probably have a multiplication to do, but we don't have a multiplier in our CPU. So what are we going to do? So that's pretty easy, I guess, for you guys. So just set up a correct full loop iterations and for one adder, right? So we can just do multiplication now. We just keep adding and until we got the final result for this multiplication. So this is basically the main ideas of how to do things in the concept of divide and conquer. And since we're talking about the divide and conquer, I have to mention about my previous PhD study. So it is the kind of like a decoding optimizations. So simply speaking, there's kind of like a lot of graphs, but never mind. I won't explain in details. But simply speaking, I was still using kind of like a divide and conquer strategies to optimize my algorithms for those decoding things. So it consists of many dedicated processors. Here we have the check node processors, variable node processors, and we need to do iteration by iteration until we meet the standard, or we kind of like we reach the maximum iteration times. So those intermediate results between different iterations will be stored in a separate storage until for the will be fetched by a next iteration of decoding. So this is basically what I did in my previous study. And back to the von Neumann architecture, what else characteristics they have? So the data programs are stored in the memory, right? So data and memory are stored in memory. And every time of execution, CPU will load a piece of the programs and then the corresponding data as well from the memory and do the execution. So this is basically how the CPU does to do these kind of things. So it also has some distinguished computing and storage. So the computation unit, or we call the control, are totally separate from the memory. So there are basically two things. So we probably have a lot of data transfer between those things. We'll be trying to solve some problems using CPUs. And now we're moving forward. So what are we going to do? And now, how are we going to implement our neural networks currently? So we use the GPU, or we call the graphic cards. So the FPGA is also kind of like a competitive platform, which I will introduce later. So the hardware layers changed from the von Neumann to what we call the near memory computing. So it is due to the reason that the most popular neural networks or transformers, probably you've heard of that. So they are likely to access all necessary data during the inference. So the putting memory close to this computing unit, it's kind of like a compromise for transformers models, more likely. Here I can give you more kind of like old news. So the AMD in 1980s, maybe 2019. It released a kind of like graphic card we call the Radeon 7, and those cards actually is embedded with we call it the HBM. It's short for the high band memory. So then suddenly next year he go back to reuse the GDDR memory instead for later products because they're cheaper. This is one of the reasons, and it's also the reason that the gaming or traditional use with these GPUs actually don't really need these high band memories or HBM. And the last layer here, what I'm going to talk about is what we call the end-to-end. So because we cannot fully approve or to how it works inside of the neural networks nowadays mathematically. So neural network models looks like a black box to us, right? So that is what we call the end-to-end. The first end is input end. The second end is output end. So inside of that is totally black box. So this is the current computer architectures. And here is how the GPU and the HBM looks like. So we have a silicon interposer. It's like a basement is colored by blue. And this is the layer of silicons used to interconnect the various dies. In this case, we have two dies. One is GPU core, and another is the die for HBM and his memory controller. So, well, if you look at the right images set, it demonstrates a CPU core with HBM memories with the red circle. It is really hardly to recognize that there are 4 pieces of VRAMs for this CPU, right? Sorry, this GPU. So this is how it works nowadays. So GPUs are designed to run neural network models nowadays, and especially transformers. And they are designed in this such kind of like a near memory computing is the optimal way. And the compute unit are surrounded by HBM. And so parameters are when we talk about parameters, where they are most likely they are the weights, feature maps, and those parameters are stored in the HBM. So when tasks are coming, the weights are brought into the computing unit, and probably for convolutional or matrix multiplications. And after that, we'll go back to the memory. So if we just shorten the path between the memory and the computation unit, we can just accelerate the whole process, right? So nowadays, all parameters, for example, probably we have 80 billions, but this number is still growing. And we need to be they need to be loaded into a computing unit when they are needed, and then the result will be output back to the computing memories. So clearly, the Neumann architecture is no longer suitable for this, right? So there's the one course this is of course drawbacks. So because I'm not a really AI expert, so it is not possible for me to show some very technical disadvantage. But however, from the point of view of the user, I think I can show you some examples. So a year ago, NVIDIA was not allowed to sell GeForce 4090 or above to China mainland for security issues, right? So I'm here not to judge whether the decision from US is good or not. But what I can say is the consultancy team and the US government, actually, they are Neumann supporters. So they banned the graphic cards for China basically based on how many CUDA cores in this graphic card it has. If it is maybe above this baseline, you're banned. If it's lower than baseline, you're allowed to sell. Well, NVIDIA actually is a really good business company. It just blocked excessive CUDA cores to meet the standard from US and keep selling those 4090D as before to China. So however, according to some resources, probably some research in China, we published. So when multiple GPUs are used in one project, the bottleneck is data transfer, not the execution CUDA cores. So those data transfer can take up to 90% of the execution time. So basically, it's hard to say that this ban is successful or not, but yeah, it totally depends on what you think. So then another thing I'm going to talk about is the GPU improvements. So if we continue using this architecture, we can only rely on those chip manufacturing technology process, like probably you heard of the 7 nanometers, 5 nanometers, 3 nanometers. But until we go to probably reach the limit, it's 1 nanometer, I guess, theoretically. So another thing I'm going to talk about is FPGA. It actually has the same architecture as GPU, but the major difference is that FPGA computation unit is fully customized and programmable. So these CLBs, marked as blue, or some more advanced units we call the DSP, short for digital signal processing, and it can be used for any operations in any data type. So for example, it can be triggered than a double precision data type or smaller than in full. So such of things. So they are fully programmable. And this is one research project for my 2 master students since the beginning of this year. So it is the competition held by AMD, and the project result can also be used for research papers. Oh, probably I forgot my card. It's okay, sorry about it. Maybe I can show you later if you are interested in that. It's really a big thing, this big. So in this project, my master students use this FPGA board provided by AMD for free, and they implement a CNN model trained by them, quantized by them, and this is designed for detecting if a real track has defects or not. So we have a camera here, right? So the FPGA part here is used to accelerate the CNN model, and there are also some embedded CPU here to handle the communication and the interaction tasks. So we cannot just light KB rail the company to break a piece of the rail for our platform to test, right? So as you can see here, we have a camera capturing those real photos, and then the photos will be sent back to our CNN model implemented in the FPGAs. And the defective rail is well, can be once those rail is detected as defective, so the platform or the car will report it to the GPS, report its GPS location to our remote server. And this GUI on the right shows the emulated place having a piece of rail. So this is central Auckland. So don't think about this rail inside of that. Just the emulated GPS location. So yeah, and so as you can see here, there are two cases and shown here. So the left one is about we have a detected or a defective rail which caused maybe takes so 590 milliseconds. And the other non-defective case is detected using 680 around maybe 700 milliseconds. So the difference, the time difference actually is caused the data transfer on the CPU, which run a Linux operating system as well. This is the reason probably. And so due to this, using this customized data type, because we are based on all projects are based on FPGAs, we can just customize the data type. So the project result has been merged into a research paper, which has been submitted to Japanese conference weeks ago. And well, because we choose to use the customized data type, and also we refurbish this computational architecture. Well, the proposed project has a better power efficiency than GPUs and CPUs. So this is because it's the advantage from the FPGA platform. And here is the demo for this project. I think I can. Yeah, a little bit. Yeah. Just basically, we have a iPad here. It's just showing the picture of the the railway, the rail tracks. When the whole system turned on. Probably just maybe mute a little bit. I heard the echo. So one start this card, start working and stop because it detects there's a railway defection. Click on the screen. And the location will be reported to our remote server. And you can see here we have some two ping pongs here. Yeah, something like that. Yeah, so it's just a very short video for that. Okay, there's another thing I'm going to talk about is another PhD student. It's still an ongoing work, research work under my co-supervision. So if you still remember this, how computation unit and memories in graphic cards interact. So in this design, we do the totally opposite way. And compared to GPUs, well, the GPU kind of like they have a fixed computation unit. They cannot be changed. But here we can be changed. So by using this FPGA architecture, so we have a reconfigurable computation unit. Here it's reconfigurable. We name it block A and B. So just instead of letting data in the memory moving out and in, so we just changed our computation unit. So for computation, here is the roughly the design of this computation flow. So the first step, at the very beginning, we configure those the computing unit. Firstly, this is the layer ones computing unit, and this is the layer 2 ones. We just simply to program those part. And now initially we got those layer 1, layer 2 computation unit. And well, then during the and then we just probably I skipped too much, but then we start to run the first layer 1's computation. And after that, we start to run to compute the layer 2's operation. So this marked as blue. And in the meantime, we can reprogram this part by giving those layer 3 computation information to this one. And in the second round, we do the same thing because in the second round, we are trying to do the computation for layer 3. And then this part become idle, and we're trying to program those part with the layer 4 computation unit, which is going to be used for next round. So those the rest can be done in the same manner. So it's just like a ping pong scheme. So by doing so, the layers are handled seamlessly. And in the best scenarios, when we are aiming to run layer 3, so for example here, when we are aiming to run layer 3 after finishing layer 2 work, so the layer 3 units has already been placed in this area to do the operation. So basically, this kind of like you need to balance the reconfiguration time and the computation time. So we have to make sure that they can be. It's better to let them to be equal. And the good thing is using FPGA, we customize our computation units, so we can reducing the complexity of computation unit for different layers. So without influencing some final result. So this is basically what we did. So the next one, the last one, or I'm going to introduce is about the future. So we are aiming to emulate the artificial brain like our real human ones, well, eventually, right? So this is our probably the ultimate goal, and probably then we have to consider what it looks like. For our group, we cannot make a conclusion what it looks like in the future, but we can estimate it has to be there has to be a training and inference model all in one, in kind of like in one of the model. So so we can do this inference probably simultaneously. We can also do the training as well. So this is the kind of like a model most likely similar to our brain. And for speak of the presentation layers, we probably need new algorithms. Those new algorithms could be developed in the future. So different from the transformer we have, and probably it's most likely still an end-to-end these problem-solving approach layers, because inside it's kind of like still a black box. So this is the future in terms of in the eye of our research group. So one of the students and our co-supervision now is trying to look for what future looks like. So the idea is coming from this if the data transfer take up 90% of AI inference currently, so why not get rid of these overhead? Why not get rid of these data transfer? So the researching in these areas actually found out we could make use of this, we call the memristors to do those. So it's kind of like a device, like resistors, but it is the inverse of the resistors. So meaning that the value G here and the inverse of the resistance R. So this is the Ohm's law, right? Probably you've heard of that. So now we start run kind of like a matrix multiplication operations like here, but it can be done by applying the voltage to each of the columns, and then we collect the current in each row. And each of the nodes has his own resistance, or we can say it's not resistance, it's the opposite of resistance. We call it the conductance. So by doing so, we can easily to do these multiplications by building this kind of like the circuit. And well, this student actually has some improvements and also some publications about to focusing on these memristors, and we call it process in memory. So when we try to save something inside of this memory, or with a memristor crossbars, and we also do the calculation as well. So there's no any data transfer again based on this architecture. So we just keep adding more memristors here, and we call the memristor. This whole architecture is called the memristor crossbars, and those complexes can be used for identifying images, and it's already done. That's this way. So I think that's all of my presentation. And the last, I want to mention that well, it's just a kind of like a brief introduction about what Bruce and I as the research team to doing and with the postgraduate student. And all these research results are still preliminary and as new academic stuff. I'm really glad to have any cooperation with you guys. So yeah, so that's all. Thank you.
Thank you, John, for the presentation, very interesting presentation. We're now open for Q&A or like discussion. Anybody have any questions for Sean? Bring forward.
Yeah, I do have questions. I know one of the drawbacks of FPGA is that the main clock rate wouldn't be so high compared with GPUs. So nowadays GPU can already reach like 2 gigahertz or something for most of the shelf FPGA, maybe just a few 100 megahertz.
Yeah, 100 megahertz.
Yes. Do you foresee that? Do you think that will be an issue? Or I mean, in terms of probably yes, GPU might not be.
Yeah. So
from the ground suitable for machine learning calculation, but do you think because of the GPU's high frequency rate, you can make up this kind of issue?
Yeah, we have the we already acknowledge that the problems because if you want to everything programmable, so you have to probably involve all of the more like the components inside of the devices. So for GPU, it's fixed. Everything is just like CPU. The whole architecture is fixed, so they can be very simple. That's the reason that they can reach probably a higher frequency of clock when they're doing the AI inference. But here, yeah, just like Elias said, we cannot reach this high, the frequency. But luckily, when we talk about the AI inference, most likely they can be fully parallel. And sometimes, especially inside of the layers, between the layers they have data dependency, but inside of layers they can fully parallel. So, but especially for some new architectures which are not optimized by the current GPUs, we can basically use our current FPGAs to emulate or to do these implementations for the new AI inference models. So this is our advantage. Another thing is I just want to emphasize again is the power consumption, because nowadays the power is not or computing power is not kind of like important. We also to be eco-friendly. So that's the one thing I have to mention about the power consumption or the energy efficiency. By using these FPGAs, we can provide a better energy efficiency compared to GPUs, which is a very power consumption, right? A consumer compared to the other things. So yeah, so also what I'm trying to say is that we also have pros and cons, and it totally depends on what we use and based on what kind of the architecture we have.
Okay, to the last thing that you talked about with the memristors, which I think is on a much lower level, because now that's basically going on the electric level. So first of all, just that I don't misunderstand this, are there now already packaged solutions for that? So are there implementations of that actually?
You mean only for the memristor?
And is actually used in this with ER? Is this the same as memristor with 4R, or is this now already a product?
It's already kind of like it's not a real product, but they have some so this company really have some product in experimental, maybe in labs for now. And one of the things I can tell you is because I'm one of the team from Tsinghua University in China, they really have a chip for memristors. They can do a kind of like image recognition. They can embed in the card. The paper has been published maybe just 2 years ago, I guess, or 1 year ago. They have the real product.
But that's of course addressing many different questions that we usually don't address. For example, the question is current versus voltage actually a good solution. I mean, this is going into the question what transistors we have. And so it's quite a different abstraction. Because I mean, so there, roughly speaking, there's a lot of change. The early transistors where there's the current driven nowadays transistors are voltage driven. It's very important for the efficiency of our computers. So well, yeah.
So I think the red noise is still kind of like experimental things in the lab, and it still needs some time to be polished. And one thing I can assure you that because those whole memoristic things actually they are in the analog world. It's not the digital again. So it's fully analog. And in the analog world, the one of the enemy for the analog is the noise. So we have probably need very good or high precision analog digital converter and digital analog converter to be connected to the digital world, right? Inside the memory state is fully analog, but if you want to connect it to the current world, you have to you use some AD converter or DA converter to communicate. That's one of the challenging things.
But we don't know whether the noise is the main problem, right? That would be just a hunch. I mean, neural networks actually rely on noise, right? There's a lot of kind of the philosophy of neural networks is kind of bringing in some stochastic elements. So the noise could be beneficial. I mean, for example,
yeah.
The current is a problem. It's simply using too much energy. So it's just probably one looking a little bit more information on that.
That's right. Yeah. We also probably just still it's too early to say that is a good choice for now. Yeah, there's a lot of things to be done.
Great. More questions for Sean?
I have a small question. Can you show the slide comparison between megahertz between FPGA and GPUs?
Oh,
yeah, that one.
That one.
So you see, like the power is even smaller, 10 times smaller compared to GPU, and probably because of the frequency of the GPU, just like 20 times higher than FPGA.
No, then you can see that the efficiency is divided by watts. So this power, of course, because we have a lower frequency, but when we divide it using a division, the GOPS divided by W by watts. So this is kind of like
yeah, but even worse, like you just 3.4 compared to 2.4 versus like 2000 compared to just 100 means that the GPU can do a lot of things compared to FPGA. Even these kind of two platforms, right?
Yeah, of course, GPU can do all things. But when we talk about the efficiency, the energy efficiency, the GPU basically cannot do anything because the whole architecture is fixed. They cannot be optimized by the researchers like us. So we can keep polishing our architecture until it's being in an optimal state, and then we can reach a better energy efficiency compared to GPU. That's probably this is the best. This is the kind of like the advantage for FPGAs, not for. But if you like Elliot mentioned that when we compare if we compare the frequency with between the FPGA and GPUs, definitely cannot beat them. Yeah.
So why is the advantage of FPGA compared to GPU?
I mean, why is it slower than GPU?
No, why is the advantage of the FPGA compared to the GPU?
You mean this one? Why is it the advantage? Or no. You mean the reason why this is the advantage or no? No,
I'm just curious. Like, for example, I want to do FPGA or GPUs. So based on this picture, it seems like GPUs clearly outperform FPGA. And I'm wondering why is the advantage of FPGA can bring?
Yeah, so first I want to say that compared to these ones, of course, most of likely we cannot compete with GPUs. But when we're talking about the energy efficiency, I mean, like how many watts it consumes per megahertz, some such of these things, right? So just for example, if we both set up those frequencies to the same value, for example, if the FPGA is the frequency is the 110, right? 110 megahertz. If we set up this CPU, if we reduce the frequency of the CPU, GPU to the same level, which is also 110, we have a better efficiency compared to GPU. So this is quite useful because it's especially for some edge computing applications, which is the power is always the first. You cannot just put a graphic card in probably in your cell phones, right? Because you know already it's really power consuming. But what we're trying to say is that if you are trying to use the FPGA, we can customize the neural networks and make it smaller and efficient, and probably it can much easier to be implemented in some edge computing devices or like the IoT. You have some smart devices, right? Currently smart devices like Raspberry Pi, they only have the CPU and a very weak GPU inside, maybe embedded GPU. But what if we put an FPGA inside? We can easily to accelerate the AI inference models. So this is what we're trying to say. So if we can only compete in terms of the frequency, of course, we're not the real competitor to the GPUs. Yeah.
I have specific questions.
Mm-hmm.
What's the price for your FPGA board, and what's the price for the GPU board?
It's cheaper than that.
Oh, really?
Yeah.
Oh, okay.
Mm-hmm. This is just a media end, so it's not really hand. Basically, the FPGA. Well, what I'm
how much does it cost?
Less than of around maybe $1,000 million, I guess.
1,000.
1,000? You can already get
Yeah. I thought it's very expensive.
No. I mean, they have different different levels because you have cost-effective ones. We only what I'm trying to say. Yeah. So these ones. Oh, this one is just $100.
Yeah, no, price is not everything. I know. Just
this is only $100. So it totally depends on what you need. So we have different type of the FPGAs. At least one of them suitable for you. Just like graphic cards. If you want to play some FPS games, then basically you need to buy the 4090, right? If only play some web-page-based games, I don't think you need to buy a GPU or a real GPU. I just use the CPU's embedded one. That's already enough. Yeah, totally depends on what you need.
So we have about 10 minutes left. Any one or two last questions? Well, I have a question, and this is sort of coming from someone not in the same background of computer science, and I think a few of us here are also not in such a background. I'm just interested in sort of the general research flow. Like, do you spend a lot of time programming logics, or do you also work on fabricating and printing the PCBs? Do you do a lot of, do you buy a lot of GPUs and do a lot of comparisons, or you also run a lot of simulations, and give some idea of the research flows? Okay, so in terms of the PCB design, actually, we don't need that. Because the AMD or Intel, actually, they provide those development boards. So basically, everything has been set up. They have the FPGAs, and they also have the board. They also have some of the peripherals. They can use such as some sensors or some cameras that's inside. So just like this one, just like this. So basically, we don't need to we just spend 0 times second we don't need any time to design a PCB or a schematic design, right? No need. And what else? Anything else? Well, just you want to share the research flow for someone who may be interested in what you're doing in the future.
Yeah. Okay. Also, I think probably you also mentioned the programming things, right? Yes, the program is actually this what I'm trying to say. If you're writing from the very beginning using these gate level implementations, definitely you need a lot of time to debug. Just like you're writing a assembly language, you need a lot of time to debug because it's too low level. But right now we luckily we have those high level synthesis code and more like C code and easy to debug and before we put it into the FPGAs. So we quite like to save a lot of time to do. Otherwise, we cannot assign those tasks to 1 year master student research.
Yeah, maybe just one last question. Okay. So you also shared a little bit about future vision, right? Of how you envision the architecture to be like. I'm not sure if it's related to what you are doing or is or anything else, but there's also been some talk about AI, so on and so forth. Is that part of your research as well, quantum computing, or is that something that you don't consider for now?
Probably it's kind of like a thing I need to cooperate with some other teams. Because the whole architecture is totally different from what we were trying to use right now and maybe in the future. So yeah, that's the kind of a thing we need to think about it. Yeah, this is really kind of like a real good topic. If we have the chance, definitely we'll do that. But for now, because I don't have any knowledge about the quantum computing. Yeah, we will think about it. Yeah, definitely we'll think about it.
Not sure if we have any stuff on quantum computing, but that would be cool.
Oh, yeah, of course. Yeah, I remember. We have, we have a lot of, yeah, I remember that we have some people
Nice.
working on the, yeah.
It's on several levels. Maybe the mean is very important.
Yeah.
It's really
Yeah.
Yeah.
It's a really good direction, yeah, to cooperate with the.
Okay, yeah. So if there are no more further questions, then thank you, Sean, for the seminar today. And this is the end of the presentation. I will also stop the recording.